Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore ammonia stripping, a guide to clearing the air in wastewater. Today, we'll be discussing an important aspect of wastewater treatment, managing nitrogen levels. While many focus on biological methods, we'll highlight a powerful alternative called ammonia stripping, which is a physical-chemical process. Over the next few slides, we'll cover how this method works, its applications, and why it might be the right choice for certain situations. So let's dive in and learn more about this effective technique. Let's talk about the core challenge we face with nitrogen management. As you know, nitrogen in wastewater creates significant environmental risks. When there's too much nitrogen, it can cause eutrophication in receiving waters, leading to harmful algal blooms, oxygen depletion, and disruption of aquatic ecosystems. To combat this, regulations on nitrogen discharge are becoming more and more stringent, which means treatment plants need to find effective ways to remove nitrogen. Traditionally, we've relied on biological nitrogen removal processes. This involves converting ammonia into nitrate through nitrification, and then transforming nitrate into nitrogen gas via denitrification. While this method works well, it's quite complex. It requires careful control of conditions, long retention times, and can be sensitive to toxic compounds or temperature changes that disrupt the process. Now, there's an alternative approach that's gaining attention: ammonia stripping. Instead of relying on biological transformations, this method physically removes nitrogen directly as ammonia gas. The key insight here is that, in many cases, it's more efficient and cost-effective to strip away the nitrogen in its ammonia form rather than converting it through multiple biological steps. This process is based on fundamental principles of gas-liquid equilibrium and mass transfer. That means it's predictable, controllable, and often more resilient to challenges that affect biological systems. For facilities with the right wastewater characteristics and operating conditions, ammonia stripping can be a powerful and practical tool for nitrogen management. Now, let's take a closer look at how ammonia stripping actually works. Essentially, it's a desorption process that relies on the chemical equilibrium between dissolved ammonium ions and gaseous ammonia. The chemistry involved is the key driver of the whole operation, so understanding that is crucial. First, we need to adjust the pH of the wastewater. We do this by adding lime or caustic soda, which raises the pH to around 10.8 to 11.5. When we make the environment highly alkaline, it shifts the equilibrium from ammonium ions, which are dissolved in water, to free ammonia gas. The higher the pH, the more free ammonia we have available for stripping. Next, the wastewater is pumped to the top of a packed tower. It's distributed evenly across the packing material, which could be plastic media or specially treated wood. This packing provides a huge surface area for gas and liquid to contact each other, which is vital for the process to work efficiently. Then comes the airflow. Large blowers force ambient air upward through the tower at quite high rates, between 300 and 500 cubic feet per gallon of water treated. This creates a countercurrent flow, meaning the rising air meets the falling water droplets. This high air-to-water ratio enhances the mass transfer process. Finally, as the wastewater flows down through the packing in thin films and droplets, the free ammonia gas transfers from the liquid into the airstream. This transfer is driven by the concentration gradient, the ammonia-rich water versus the ammonia-free air. Once the ammonia is transferred, it is carried out through the tower exhaust and released into the atmosphere. Overall, this process effectively removes ammonia from wastewater by leveraging chemistry and engineering principles to maximize gas transfer. When considering ammonia stripping, it's important to understand the ideal concentration range where this process is most effective. Typically, wastewater with ammonia nitrogen levels between 10 and 100 milligrams per liter is the sweet spot. If the ammonia concentration drops below 10 mg/L, the process tends to become inefficient and may not be cost-effective compared to other treatment options. Conversely, if levels go above 100 mg/L, other technologies like steam stripping, ion exchange, or breakpoint chlorination might deliver better performance and economic benefits. At very high concentrations, the costs of air stripping escalate because you'd need to move enormous volumes of air, which quickly becomes impractical and expensive. Another key advantage of ammonia stripping is its robustness in handling toxic waste streams. Unlike biological treatments that can be easily disrupted by substances like heavy metals or organic solvents, ammonia stripping is largely unaffected by these toxins. Its physical-chemical nature means it can treat industrial wastewaters containing these inhibitory substances reliably. This makes it particularly valuable for industries such as chemical manufacturing, pharmaceuticals, and metal finishing, where wastewater often contains complex or toxic compounds. Controlled, selective removal is also a major benefit. Unlike biological systems that require a full nitrification and denitrification process, ammonia stripping allows precise control over how much ammonia is removed. By adjusting parameters like pH, airflow, and hydraulic loading, operators can target specific ammonia levels in the effluent. This flexibility is especially useful if regulatory permit limits change or if only partial removal is needed. Plus, the process doesn't produce a backwash stream that needs additional treatment, and it can be easily paused or restarted as needed. Finally, climate considerations play an important role in the process's efficiency. Ammonia stripping works best in warm, temperate climates where winter temperatures stay moderate. Facilities located in southern regions or those with enclosed, heated towers can maintain consistent, year-round performance. Keep in mind, even small drops in temperature can significantly reduce removal efficiency because of the exponential relationship between temperature and process performance. In regions with sustained freezing conditions, biological treatment might become a more practical choice despite its limitations, because low temperatures make ammonia stripping less effective. Let's now look at some of the critical disadvantages and limitations of this process. First, temperature dependency is a major factor. Performance drops significantly as temperatures decrease. For example, at 20 degrees C, we can expect about 90 to 95% removal efficiency. But when temperatures fall to around 10 degrees C, that efficiency drops to roughly 75%, and near freezing, it becomes almost negligible. Cold weather also causes icing on the packing, fogging that reduces visibility, and even potential tower shutdowns. Some facilities need to enclose the towers and include heating systems, which can greatly increase both capital and operating costs. Next, there's the issue of air pollution transfer. It's important to understand that ammonia isn't destroyed in this process. It's simply transferred from water to air, often at concentrations around 6 milligrams per cubic meter. This can lead to violations of air quality regulations, especially in areas that already struggle with pollution. Neighboring communities might object due to ammonia odors, and some jurisdictions now require additional treatment like acid scrubbing for the exhaust air. This adds complexity and cost. Plus, environmentally, it's questionable because you're just shifting pollution from one medium, water, to another, air. Then we have scaling and fouling issues. When water has a high pH, typically between 10.8 and 11.5, calcium carbonate can precipitate out and deposit on the packing material. This reduces the efficiency of the process and increases pressure drops across the tower. To keep things running smoothly, cleaning might be needed monthly or quarterly, depending on water hardness. Removing scale usually means shutting down the tower for manual cleaning or chemical treatment, which is labor-intensive and generates waste. And it's not just calcium carbonate. Magnesium hydroxide and other compounds can also precipitate, creating ongoing maintenance challenges. Moving on, high energy consumption is another significant concern. Because the air-to-water ratio can be as high as 300 to 500 to 1, large blowers are needed, which consume a lot of electricity. Pumping water to the top of the tower adds to the energy costs as well. Monthly electric bills can become quite substantial, especially with fluctuating energy prices. Plus, this process leaves a sizable carbon footprint, which may conflict with sustainability goals. And we can't forget the noise. Blowers often produce sound levels above 85 decibels, requiring sound attenuation measures and potentially causing community relations issues. Another limitation is incomplete nitrogen removal. This process primarily targets free ammonia, or NH3, but it doesn't effectively remove organic nitrogen, nitrites, or nitrates. If your wastewater contains significant amounts of these other forms of nitrogen, or if you need to meet strict total nitrogen limits, additional treatment steps are necessary. Sometimes, biological polishing or other technologies have to be added to achieve the desired nitrogen removal. Finally, there are chemical handling risks to consider. Lime and caustic soda are both corrosive and hazardous materials. Operators require proper safety training and protective equipment to handle these safely and avoid burns or spills. Storage facilities must comply with fire and environmental regulations. The costs for chemicals can fluctuate, and lime slaking, where lime is mixed with water, generates heat and demands specialized equipment. Spills of caustic chemicals can cause serious environmental damage, adding another layer of operational complexity. So, while this process offers benefits, it's important to carefully weigh these disadvantages and limitations within the broader context of your treatment goals and operational capabilities. Let's now look at the design criteria that make ammonia stripping systems effective. As you can imagine, creating a successful system requires careful attention to multiple parameters, because each variable impacts how well the ammonia is removed, as well as the operating costs and ongoing maintenance. Engineers need to find the right balance among these factors to optimize performance. First, let's discuss the hydraulic loading rate. The recommendation is typically 1 to 2 gallons per minute per square foot of tower cross-sectional area. If we go lower, we often see better removal efficiency, but that means a larger tower and higher capital costs. Conversely, higher rates reduce costs but can lead to problems like flooding or channeling in the packing. The key is to find that sweet spot where efficiency and economics align, which depends on ammonia concentrations, removal goals, and the type of packing used. Next, the air-to-water ratio is crucial. Maintaining around 300 to 500 cubic feet of air per gallon of wastewater is essential because it creates the concentration gradient needed for effective mass transfer. If we operate at lower ratios, we save energy but risk severely compromising the removal efficiency. Also, in cold weather, we need to increase this ratio to compensate for reduced vapor pressure. Keep in mind, blower sizing, which impacts this ratio, is a significant capital cost. Moving on to packing, depth and type matter a lot. Usually, we specify about 20 to 25 feet of packing depth to ensure sufficient contact time. Modern plastic media, like polypropylene or PVC, provide high surface areas, around 30 to 60 square feet per cubic foot, are lightweight and resist corrosion. Structured packing tends to be more efficient than random packing, but comes at a higher cost. Alternatively, wood slats treated with preservatives are cheaper, but require more maintenance. The packing must also withstand high pH levels and allow for even liquid distribution. When it comes to tower configuration, countercurrent towers, where air enters at the bottom and water flows from the top, generally outperform cross-flow designs by about 10 to 15% in efficiency. The tower diameter usually ranges from 10 to 30 feet, depending on flow rates, and materials like fiberglass reinforced plastic are common because they resist the alkaline environment. Also, including mist eliminators at the top helps prevent water carryover and ice formation issues. There are additional considerations, such as pH control systems that automate lime or caustic addition, maintaining the pH in the 10.8 to 11.5 range, which is optimal for ammonia removal. Uniform water distribution is achieved through spray nozzles or weirs. For low-flow situations, recirculation systems can enhance hydraulic loading. In cold climates, winterization, like enclosures, heating, or insulation, is important. And of course, instrumentation such as flow meters, pH probes, temperature sensors, and pressure monitors helps keep everything running smoothly. Now, regarding performance, under ideal conditions, say at 20 degrees Celsius, pH around 11, and with an air-to-water ratio of 400 to 1, we can expect ammonia removal efficiencies of around 90 to 95%. That means reducing a 50 mg/L influent to just 2.5 to 5 mg/L in the effluent. But of course, actual results can vary depending on temperature, alkalinity, and how well maintenance is performed. To account for uncertainties, we typically include safety factors of about 1.2 to 1.5 in our design to ensure reliable operation. All of these factors are interconnected and vital for designing an effective ammonia stripping system. By carefully balancing them, we can achieve both high removal efficiency and cost-effective operation. Operation and maintenance requirements are absolutely critical for ensuring reliable ammonia stripping performance. Unlike biological systems that can sometimes self-regulate, physical-chemical processes demand consistent attention from operators and proactive maintenance to prevent performance issues and costly repairs. Let's start with daily operations. Operators need to monitor pH levels continuously and record these readings, adjusting chemical feed rates to keep pH within the optimal range of 10.8 to 11.5. It's also important to check air and water flow rates against the design specifications, as deviations can impact efficiency. During daily inspections, look out for unusual noises, vibrations, or visible ice formation in the tower. Verify blower performance and motor amperage to ensure everything is operating smoothly. Monitoring the effluent ammonia concentration, either through grab samples or online analyzers, is essential. And of course, all these readings should be documented daily, not just for regulatory compliance, but also for tracking trends over time. Moving on to weekly inspections, these are more detailed. You should visually inspect the distribution system for clogged nozzles or uneven water distribution, which can reduce efficiency. Check the packing material for signs of scale buildup or channeling, as these can hinder gas transfer. Also, inspect blower oil levels and belt tensions, and test backup chemical feed pumps to make sure they're ready if needed. Keep an eye on pressure drops across the tower. An increase often indicates scale accumulation. Take a close look at structural components for signs of corrosion, and don't forget to clean strainers and filters. Ensuring safety equipment is fully functional is also a key part of these inspections. Monthly maintenance involves more thorough work. This includes lubricating equipment according to manufacturer specifications, calibrating pH probes and flow instruments to ensure accuracy, and cleaning scale from accessible packing sections, using high-pressure water or mild acids as needed. Service blower intake filters, test the chemical feed system's accuracy, and inspect electrical connections for any corrosion or looseness. It's also wise to review energy consumption trends, as increased energy use can signal underlying issues. Any repairs identified during inspections should be scheduled promptly to keep everything running smoothly. Quarterly activities are more intensive. They typically involve a major cleaning of the tower, which might require shutting down the system partially or completely. Remove and thoroughly clean the packing material, either in place or after removal to a cleaning pad. Descale with appropriate acidic solutions, like hydrochloric or sulfamic acid, followed by neutralization. Inspect internal components such as mist eliminators, perform motor Megger testing to check insulation resistance, and review the spare parts inventory. This is also a good time to perform preventive maintenance on pumps, including replacing seals if necessary, and to conduct operator retraining sessions to ensure everyone is up to speed. Finally, the annual overhaul is the most comprehensive. It involves shutting down the entire system for major maintenance tasks. During this time, thoroughly inspect and replace damaged packing, overhaul blowers including bearings, rebuild chemical feed pumps, and inspect the tower structure, recoating exposed areas if needed. Worn instrumentation should be replaced, safety interlocks tested, and all system modifications documented in updated O&M manuals. This is also an opportunity for a full operator training review to refresh skills and knowledge. And I can't stress enough, safety first. Handling chemicals like lime and caustic soda requires strict safety protocols. All operators should wear appropriate PPE, including face shields, gloves, and protective clothing. Establish confined space entry procedures for tower maintenance, and keep eyewash stations and safety showers nearby. Regular training on chemical hazards and emergency responses is essential. Store safety data sheets where everyone can access them easily, and conduct safety drills regularly. Keeping safety at the forefront helps prevent accidents and ensures a safe working environment for everyone involved. Let's take a closer look at how temperature impacts ammonia stripping performance. Temperature is actually the most critical factor influencing how effectively we can remove ammonia. The relationship here is exponential, meaning small changes in temperature can have a big effect on efficiency. This makes the process highly sensitive to seasonal variations and climate conditions. If we look at the chart, it shows how ammonia removal efficiency varies across different temperatures under standard operating conditions. pH 11, a 400-to-1 air-to-water ratio, and a hydraulic loading of 1.5 gallons per minute per square foot. What's striking is the sharp decline in performance when temperatures drop below 15 degrees Celsius, or about 59 degrees Fahrenheit. That's why choosing a site with a suitable climate is so important. Now, why does temperature matter so much? As temperature goes up, the Henry's law constant for ammonia increases exponentially. That means more ammonia volatilizes at a given concentration, making removal easier. Also, the vapor pressure of ammonia rises with temperature, which creates a stronger driving force for mass transfer from liquid to gas. Higher temperatures also reduce water viscosity, which improves film coefficients and speeds up the mass transfer process. In practical terms, a 10 degrees Celsius increase can nearly double the removal efficiency within the typical operating range. But it's not just about performance. Cold weather introduces several operational challenges. Icing can form on tower packing and structural parts, which might even cause structural failure. Fogging from the exhaust air can impair visibility on nearby roads, creating safety hazards. Freezing can damage instrumentation, burst pipes, and immobilize critical equipment. That's why facilities in colder climates need to plan ahead with winterization strategies. These might include installing tower enclosures with environmental controls, adding supplemental heat to the air or water streams, insulating piping and equipment, or even shutting down operations seasonally and switching to alternative treatment methods during winter months. Understanding how temperature influences ammonia stripping helps us optimize performance and ensure safe, reliable operations year-round. Let's take a closer look at the cost considerations and economics involved in choosing a treatment method. First, the capital cost per GPM for a complete system treating between 100 to 500 GPM typically ranges from $150 to $400. This includes all major components like the tower, packing, blowers, chemical feed systems, instrumentation, and installation. Then, on the operating side, you're looking at about $2 to $6 per 1,000 gallons. This covers electricity for blowers and pumps, chemicals such as lime or caustic, labor, and routine maintenance. As for the system's lifespan, with proper maintenance, you can expect around 15 to 20 years before major equipment replacements are needed. Now, when comparing treatment options, it's important to consider the full life cycle costs, meaning both initial investment and ongoing operational expenses, along with factors like regulatory compliance and site-specific constraints. Ammonia stripping, for instance, has moderate to high capital costs but moderate operating costs, mainly because it's energy-intensive. It requires a large tower structure but is toxin-resistant and provides predictable results. However, it's weather-dependent and can produce air emissions. Biological nitrification denitrification has moderate capital costs and low to moderate operating costs. It needs a large basin volume, but offers complete nitrogen removal without air emissions. The downside is that it's sensitive to toxins and has a slower startup time. Breakpoint chlorination is the least expensive to install, with low capital costs, but it has high operational costs due to chemical expenses. It requires a small contact tank and is reliable and simple to operate, but it involves expensive chemicals and produces disinfection byproducts. In general, for facilities with moderate ammonia loads, say 20 to 60 mg/L, especially in warm climates, ammonia stripping often turns out to be the most cost-effective option. Its higher initial cost is offset by operational reliability and less vulnerability to biological failures. However, in colder climates, or where strict air quality regulations are in place, biological treatment might be more economical despite its limitations. So, choosing the best method really depends on balancing these costs, environmental factors, and regulatory requirements. The bottom line is making the right choice. Ammonia stripping is a proven and robust technology for nitrogen removal in certain applications. Its physical and chemical nature offers advantages that biological systems just can't match, especially when dealing with industrial wastewaters that contain compounds toxic to microorganisms. But of course, success depends on careful evaluation of site-specific factors before moving forward. So, when should we consider ammonia stripping? Typically, it's suitable when ammonia concentrations are between 10 and 100 milligrams per liter. It's also a good option if there are toxic compounds present that inhibit biological treatment. Warm climates with minimal freezing conditions are ideal, as well as having enough land available for the tower installation. And importantly, there should be no restrictive air quality regulations related to ammonia emissions. It's particularly useful when operational flexibility is needed, such as for quick startup and shutdown, and when skilled maintenance staff are available for regular upkeep. On the other hand, there are situations where alternatives might be more appropriate. For example, in cold climates with extended winter freezing periods, ammonia stripping becomes less feasible. Strict air quality regulations limiting ammonia emissions can also pose challenges. If ammonia levels are very high, above 100 milligrams per liter, or very low, below 10 milligrams per liter, other methods might be better suited. Additionally, if total nitrogen removal, including nitrate and nitrite, is required, or if there are limited maintenance capabilities or budget constraints, we should consider other options. High energy costs that make operation uneconomical, or community concerns about odor and air quality impacts, are also important factors to keep in mind. Before making a final decision, it's essential to carry out a thorough pre-implementation analysis. This includes bench scale or pilot testing with your actual wastewater to verify removal efficiency and identify operational challenges. Analyzing climate data over multiple years helps us predict seasonal performance. We also need to review air quality regulations at federal, state, and local levels to understand discharge limits and permitting requirements. Evaluating the total life cycle costs, including capital, energy, chemicals, labor, and maintenance, against alternative technologies is crucial. Assessing the skill level of operators and their training needs for safe chemical handling and process control is another key step. We should also consider community relations, especially since the towers are visible and could generate odor complaints. Developing contingency plans for cold weather operation or equipment failures ensures we stay compliant and maintain reliable treatment. Remember, ammonia stripping isn't a universal solution, but when applied under the right conditions, with proper design and committed maintenance, it delivers reliable, cost-effective nitrogen removal, something biological systems don't always match. The key is an honest assessment of site conditions and operational capabilities before choosing this technology. With thorough evaluation of wastewater characteristics, local climate, regulatory landscape, and available resources, ammonia stripping can be an excellent choice for nitrogen management. Its resilience, predictability, and independence from biological vulnerabilities make it a valuable tool for us as wastewater treatment professionals when deployed under the right conditions.